So, let us look into a generalized linear discrete time model. Often we will find these models very useful in practice. So, the general equation for a linear discrete time model is given by summation a k y of n minus k going from 0 to p equals summation b k f of n minus k equals 0 to q. So, this f is basically the input or the forcing function, and this is the output, y is the output which self expresses itself with the various delays, it self expresses itself with various delays. Now, when p equals 0, equation 1 is a moving average. So, when p equals 0, basically you just are looking at one term, right, and the scalar a naught can be pulled outside. So, you just have y n, and this is basically the average of the forcing function, and the average there is some weight to this average via these bk's. So, when p equals 0, equation 1 is a moving average signal. Since we scale the input over a q plus 1 window, q plus 1 because from k equals 0 to q you have q plus 1 points. So, therefore, over a q plus 1 window you are going to average the signal. Now, when q equals 0 with a naught equal to 1, this is interesting because we have y of n equals b naught f of n minus summation a k y of n minus k going from 1 to p. Okay. Now, just rewriting this equation again, right. So, this is the forcing part, and the output at time n depends upon the previous outputs at various time delays at n minus 1, n minus 2, n minus 3, so on. So, this is essentially an auto regressive model. So, this general equation is basically the autoregressive moving average model, and it is also called ARMA model, autoregressive moving average. So, when p equals 0 it becomes moving average, when q equals 0 it becomes autoregressive, right. It is autoregressive model of order p. Why it is called autoregressive? Because this signal y of n self expresses itself, it self expresses itself, and therefore, it is called an autoregressive model. And these models can be expressed in the form of a signal flow graph that all of us are familiar from undergraduate signals and systems. So, let us try to realize the system as a signal flow graph. Okay, now how do we get this graph? Now we have various tab delays. Now we have a forcing function f of n. At this point it is scaled by b0 and gets to the output. Then f of n going through this delay is f of n minus 1, f of n minus 1 is scaled by b1 and then gets to the output, so on and so forth. You can think of having all these gains b0, b1, b2, so on taken off at various tab delays, they get summed. So, that is one component for y of n, but also y of n can be expressed as a regression from the outputs at various other delays, right. So, therefore, now from this delay you can have a feed, this is a feed forward path. I am giving you the arrows in the forward direction, that is why it is a feed forward path, plus we also have a feedback path, right. From this delay there is a feedback path. We have a minus a1 as a gain, it just goes back into the feedback path, and then at this point we have minus a2 as a gain, and that gets to the feedback path, and so on and so forth. Basically at various tab delays you should have a feed forward path and you have to have a feedback path, and that is a general form of a signal flow graph for realizing this ARMA model, right, autoregressive moving average model. And this is very useful because in the later part we will build the state space representation for this generalized discrete time model, and we will analyze this more carefully through subsequent lectures. So, we will stop here.